SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. Welcome to this course Power Plant System Engineering Module 2 Vapor Power System Part 1. So, in this lecture we are going to study the most important cycle that are used for steam power systems, that is Rankine cycle. In this Rankine cycle, we are going to study its theoretical modeling, thermodynamic cycle analysis, and we also need to study the different operating parameters for this Rankine cycle. Subsequently, we are going to discuss about the effect of irreversibility, losses, process inefficiency, how they are going to affect the cycle. For that, we also need to see the effect of condenser and boiler pressures and how the changes in these pressures is going to have a net effect in the Rankine cycles. So, these are the summary of the today's lectures. Now, let me start the first topic, that is modeling of Rankine cycles. In our previous lectures, I emphasized about the Carnot cycles, and there we have summarized that Carnot cycle is not possible for its implementations in the practical aspects. So, cycle needs to be modified so that its practical utility is ensured. To summarize some of the important inferences, the first thing that I need to emphasize is that the cycle efficiency for Carnot cycle is almost impractical, but we can do some logical modifications through a Rankine cycles, and in fact, it meets many practical needs, demands to improve the effectiveness. But at the cost of these modifications, the net effect of Rankine cycle is that its efficiency will be smaller than the Carnot cycles. So, just let us understand this, why it is smaller than Carnot cycles, because if you look at the TS diagrams, the two temperature limits TA and TB, TA is the upper temperature, TB is the lower temperatures, and on this cycle if a Carnot cycle is to operate, then we can find out its efficiency. So, since it is a TS diagrams, area under this cycle will give you the net heat transfer. So, the heat addition process in this Carnot cycle is this Q12. Now, subsequently when you move on to Rankine cycles, the cycle gets modified as 1, 2, 3, 4, 5. Why? I will come back to this point later, and through these things what we will see is that the area under the curve, that is heat addition process from 5, 1, 2, if you calculate for this Rankine cycle, it is always higher. So, comparing this net heat input when it is higher, the thermal efficiency will also be lower. But the advantage that we get is in the form of work ratio or work output. If you make a comparison of work output, since it is a cyclic process, so net heat transfer is also equal to net work. So, for this Rankine cycle, this area is higher. So, obviously, this work output for Rankine cycle will be higher as compared to Carnot cycles. So, this is the basic advantage that we get just by modifying little bit in this Rankine cycle. Now, what did we do in this modification is that if you compare this Carnot cycle, that is 1, 2, 3, 4 and Rankine cycle, that is 1, 2, 3, 4, 5 and 1. So, if you compare these three and if I just drop a vertical from point 1, it comes as 4 dash. So, effectively if you compare in this cycle, Carnot cycle is 1, 2, 3, 4 dash. So, we simply did that 0.4 dash was shifted to 0.4. What it means in terms of practical utility is that at 0.4 dash the state of working fluid is in the liquid vapor regions. So, when you move to 0.4, it is now saturated liquid, and handling this saturated liquid is much easier than the handling liquid vapor things, and for that also pumping process will be easier. So, because of these reasons the Carnot cycle was shifted to Rankine cycles. In addition to that, we also have to see the fact that your heat addition process in the Rankine cycle is increased, because heat addition process if you look at, there is 4, 5 and 1. In this heat addition process, what happens is that at constant pressure, that is in a TS diagram and under constant boiler pressures, the system goes from heat addition process goes from 4 to 5, and from 4 to 5 it is essentially we are adding heat to bring the state of liquid to state of saturated vapor at 0.5. So, and from 5 to 1 it is again inside the dome. So, it is a liquid vapor region. So, this is the additional process. Now, looking at its implication in terms of its uses, what we think of is that this entire vapor power plant consists of 4 principal components. That means, to make this work in a actual power plant, we need to think about 4 principal components, and in fact, this is one of the basic requirement for a vapor power plants. So, the components are turbine, condenser, pump and boiler. These are the 4 major components, and it is presumed that all these components operate in a steady state manner. Other assumptions that we make, that changes in the kinetic energy, potential energy, and in wherever there is a unavoidable heat losses, they are neglected, and energy transfers is either interpreted as work or heat, and they are considered component wise. And once we consider the component wise, then we can bring out the total informations about the overall systems. Now, let us understand the each component one by one. First one is the turbine. So, you look at this cycle, that what happens in a turbine. In a turbine, steam enters in the turbine. In ideal Rankine cycle, saturated steam at 0.1 enters in the turbine, and after expansions the steam loses all its energy. So, it comes to the state point 2. So, that means 1 to 2 process is the isentropic expansion in a turbine. Then from 2 to 3, the state of 2 is in the liquid vapor regions, and from 2 to 3 the steam loses heats in a condenser, and this condenser process is a constant pressure process. Finally, the state of the working fluid is at 3, which is saturated liquid or saturated water. So, the process in the condenser, and that means condensate leaves at state 3, then it enters to the working feed pump. So, when it enters to the pump, it is in the saturated liquid state. So, its pressure is increased. So, how much it is increased? It is increased to boiler pressures. So, 0.3 to 4 it is a process in the pump, and this process is also modeled as isentropic. Then from 4 to 5 and subsequently to 1, it is a heat addition process. So, from 4 to 5 the heat addition process takes place to bring the liquid water to the saturated vapor, and from 4 to 5 it is the liquid water goes to saturated liquid at 5. Then from 5 to 1 saturated liquid goes from state 5 to saturated vapor at state 1. So, 4-5-1 process, entire process that happens in the boiler, and it is essentially what we call as Q in, and again the cycle continues when the steam enters in the turbine. So, heat addition process that comes from 4, 5 and 1, heat rejection process that happens in the condenser, that is Q out, and your turbine work comes as W T in the state 1 to 2, and pump work which is input required, it is W dot P. So, if you want to make a steady state energy balance equations component wise, then we can bring down these expressions. For condenser, it is Q dot out by m dot is H2 minus H3, that is done per unit mass basis. Now, for turbine, it is W dot T by m dot is equal to H1 minus H2. Then for pump, we can write it as W dot P by m dot is equal to H4 minus H3, and for boiler, it is Q dot in by m dot is H1 minus H4. And in fact, many times when the pump feeds the water to the boiler, we call this as a feed pump, and also whatever the working fluid enters into the boiler, we call this as a boiler feed water, BFW. Then we need to find out the performance indicator. The performance indicator for this Rankine cycle, we can go through the cycle 1, 2, 3, 4 and 5, then 1, 2, 3, 4, 5 and 1. But now if you want to calculate one by one thermal efficiency, in fact all the performance parameters I have already mentioned earlier, they are thermal efficiency, then turbine work, pump work, then net work, then work ratio, then back work ratio, and specific steam consumption and heat rate. These are the some of the performance indicator for a steam power plant. So, these things can be calculated by using Rankine cycles. So, first one is thermal efficiency, that is net work by heat input. Second one is work ratio, W net by W T, and W net is nothing but turbine work minus pump work. The other interpretation of work ratio is the back work ratio. Many books interpret as a back work, that is pump work to the turbine work. So, both have same meaning. So, ideally speaking, our work ratio should be higher or back work ratio should be as much small as possible. The other important aspect is specific steam consumptions, that is interpreted kg per kilowatt hour, and again heat rate, that is nothing but the Q input per kilowatt hour. Then we will try to see what is ideal Rankine cycle. So, the ideal Rankine cycle, already I have done the thermodynamic analysis, but some of the other reference is that the system is idealized with a viewpoint that there is no irreversibility in the cycle. So, irreversibility, I mean if I say boiler pressure is 30 bar, so there is no fluctuation in this boiler pressure, and if I say the condenser pressure is, let us say, atmospheric, there is not fluctuating this condenser pressures. But there are irreversibilities, losses in the piping systems that is introduced in practically, that is one aspect. Other aspect is that when this turbine and pump they operate, they may not operate at its full capacity or full efficiency. So, we introduced these things as an internal effect which drops down the overall performance. So, for that irreversibilities are comes into pictures. So, when I say ideal Rankine cycle, the cycle is free from all these uncertainties in terms of irreversibilities. So, in that case, what we really say that for an ideal Rankine cycle which we have analyzed its thermodynamic property or behavior and cycle analysis, what we have assumed is that it is an isentropic expansion in the turbine, then the heat transfer of working fluid in the boiler as well as in the condensers, they occur at constant pressures. Then we have isentropic process in the pump. So, instead of expansion I should write isentropic process in the pump in the compressed liquid regions. Then the heat transfer to the working fluid at constant pressure through the boiler. So, all these things, heat addition process or heat rejection process takes place at constant pressure, and the pump and turbine process, they are treated as isentropics. Okay. But there are some situations we also say that instead of an ideal Rankine cycle can be also thought of, instead of saturated steam at state 1, we can add some degree of superheat. So, the state of steam can lie in the superheated region, that is 1 dash, and there the turbine process can start. So, ideally speaking 1 to 2 or 1 dash 2 dash, they are the process in the turbine. The very basic difference that we get, that steam at state 1 is heated further before being expanded in the turbines. So, the advantage that we get is that this vertical line, length of this vertical line is higher. So, we can extract more work, number 1. Number 2 is that there is a chances that we are going towards the saturated vapor region, that means 2 moves to 2 dash. So, through this process we can effectively handle the quality of the steams. So, we will give more details in the subsequent lectures where we introduce the term superheat. But anyway, now moving further, this is all about the ideal Rankine cycle. Other process of idealization is interpreted in terms of pump work. Now, if you recall our thermodynamics viewpoint, we say that pump is idealized to operate without any reversibilities, and in fact, when you say pump, it handles liquid and which is in general incompressible. That means its density or specific volume do not change. So, if we can idealize this pump process, which is, we call this as a internally reversible adiabatic process, which means internally isentropic process, then we can frame these equations or the thermodynamic equations gets modified. So, if you recall our TdS equation, which says that TdS is equal to dH minus Vdp. Now, in this case at constant entropy, so when this ds goes to 0 in an isentropic process, so dH is equal to Vdp. Now, if we apply these equations for the pump, the states points for the pump is 3 and 4. So, we rewrite this equation as H4 minus H3 as integral of Vdp, and H4 minus H3 is nothing but input work per kg of fluid or water. So, this becomes W dot P by m dot is H4 minus H3. So, that is nothing but integral of Vdp. Here the assumption makes that since we are handling liquids in the pump, the specific volume do not change, it comes out of the integrals. So, the working expressions for pump work boils down to V3 into P4 minus P1. So, this pump equation can be effectively used, because normally we know the operating pressures, that is P4 minus P3. So, this is what the idealization of pump work. Then we will move on to, when you say idealizing these things pump work, let us see how this Rankine cycle gets compared with respect to Carnot cycles in terms of performance calculations. So, first thing that we need to see, in fact, I have already told that work ratio or work output for Rankine cycle is higher, but the thermal efficiency is lower for Rankine cycle in comparison with the Carnot cycles. This is already interpreted, but the other side of the story is that if you really need to see the difference between Rankine and cycle and Carnot cycles, the Carnot cycle does not have much flexibility. So, what does this mean? That when you say this Carnot cycle in a TS diagrams, when you say this Carnot cycle as 1, 2, 3 dash and 4 dash, the expansion work and this compression work, they are more or less effectively of same order. So, it has no meaning as far as its practical utility is concerned, and main reason being that point 3 dash is shifted to point 3, and when it is shifted to point 3, you can deal with easily by using a pump. You can deal the working fluid, we can increase the pressure of the working fluid to using the pump. The other thing is that now when from 4 to 4 dash, in this process we are adding heat in a Rankine cycle, we are adding heat externally, so that liquid at state 4 becomes saturated liquid at state 4 dash. And in fact, in reality this heat addition is normally done through the waste heat or some of the combustion products that goes out of the systems, that is effectively utilized in this heat addition process. But this flexibility is not there in the Carnot cycle. So, that is the main issues that Carnot cycle, why it is not practically feasible. Other option is that the Carnot cycle does not have a flexibility to use single phase systems, which means state 3 dash in a Carnot cycle is in liquid vapor regions. We need to establish the quality of the state of the working fluid at state 3 dash, but this issue can be resolved by moving this 3 dash to 3, because information at 3 is known as a saturated liquid. So, this allows that we need to condense the vapor completely, handle only liquid as it is done in the Rankine cycles. Pumping from 3 to 4 in liquid phase and heating without work from 4 to 4 dash are the processes that can be easily achieved in the practice. So, 4 to 4 dash can be achieved externally through external heating process, through the waste heat or some through by another mechanisms, which is effectively does not come into the performance calculations. So, this is what we get the benefit out of these Carnot cycles. Now, let us move on to the thermodynamic angle of these Carnot cycles. Now, in a Carnot cycle we cannot play with the operating pressures. It is very difficult to play with the operating pressures, because if you look at the efficiency term, the efficiency of the Carnot cycle is 1 minus Tc by Th. Tc stands for the lower temperature, Th is the higher temperatures. So, efficiency can be increased by two ways, one by increasing the Th, other is by reducing Tc, and reducing Tc is not possible, because when reducing Tc means the lower limit is fixed with respect to atmospheric conditions, but increasing Th is possible. So, if you plot the efficiency versus Th for a given Tc, then what we can get a curve like this, which says that with increase in the Th, that means with increase in the heat addition, your cycle efficiency goes up, Carnot cycle efficiency goes up. Now, we are going to apply same logic for the Rankine cycles. So, for that purpose we need two important observations, because the Rankine cycle consists of the components like boiler, which operates at higher pressure, and condenser, which operates at lower pressure. Now, let us see what is the effect of increase or decrease of boiler pressure or condenser pressures. So, there are two possibilities here. So, first thing, that to get a better efficiency or higher to efficiency can be higher by reducing Ts, Tc or increasing Th. Now, in this Th for us is nothing but its correlation is with respect to boiler. So, this Th is dependent on or higher temperature of heat addition, nothing but the which is dependent on boiler operating pressure, and Tc is nothing but which is linked to condenser pressure. So, our job is to reduce Tc or increase Th. So, in one case what we have shown is that let us fix the condenser pressure, that means Tc is fixed. At fixed condenser pressure we are exploring the how this Rankine cycle looks like. So, when your ideal cycle of ideal Rankine cycle would be 1, 2, 3, 4 and 1, that is normal working cycle. Now, if I am increasing the boiler pressures, so the cycle now becomes 1 dash, 2 dash, 3, 4 dash. Now, in this process what did you do? Your mean temperature of heat addition gets increased. So, as a result Q in also increased. When Q in increased, your efficiency also increases. So, it means increasing the boiler pressure for an ideal cycle tends to increase the thermal efficiency. The other side of the story is that when we say actual Rankine cycle for a fixed boiler pressure, if I drop this condenser pressure down, which means that in normal circumstances the water should come down at P atmospheric, but intentionally I keep this condenser pressure below atmospheric, so that 2 becomes 2 double dash. So, initial cycle which is 1, 2, 3, 4 and 1 now becomes 1, 2 double dash, 3 double dash, 4 double dash. So, when this condenser pressure reduces, it tends to increase the thermal efficiency. So, that is the reason all steam power plant always operates at the most possible or the lowest possible temperature, which is the condenser pressures, and this is close to maybe 0.008 bar or 0.04 bar, something in that range, and this is generally done to improve the cycle efficiency. So, whatever I have explained, if I just summarize that the lowest feasible condenser pressure is the saturation pressure corresponding to ambient temperature, and that is the lowest temperature heat rejections from the turbine. But ideally liquid water at atmospheric pressure could be done directly by boiler or pump or steam and can be discharged to atmosphere by the turbine exit. By including a condenser in the steam side and operating below atmospheric pressure will lead to discharge of the steam turbine at lower pressure regions, thereby improving the thermal efficiency. Another part is that addition of condenser allows to operate in a closed loop, and it permits the less corrosive than the tap water. So, because of these reasons, the thermodynamic aspects always says that the higher boiler pressure or lower condenser pressure is the essential motive for the thermodynamic analysis of a steam power system in operating in Rankine cycle. Now, apart from that, now we are going to look into other possibilities, and that other possibilities we categorize as irreversibility and losses. When I say irreversibility and losses, it is categorized in two effects. One is internal effects, other is external effects. So, let us understand what is this external effects. So, normally high temperature regions, that is the boiler pressure and condenser pressure is the low pressure regions, and we ideally we say they have to operate at constant pressure, but due to the frictional losses, frictional effects and the piping systems, losses in the piping systems, there is a drop in the pressure, and these are categorized as external effects, and the tendency of this external effect is to drop the net power or net work output, and also they also tend to drop the thermal efficiency. And when you say internal effects, the internal effects mainly is interpreted in terms of process inefficiency, which is introduced in turbines and pump. That means, we say that turbine operates in isentropic manner. Now, what happens if they operate in non-isentropic manner? Similarly, pump operates in isentropic manner. What happens if it does not operate in isentropic manner? So, for that reasons we introduce the term called as isentropic efficiency, and through this isentropic efficiency we can easily calculate or easily quantify the thermodynamic effects of Rankine cycle by inclusion of irreversibility and losses. So, to do that, for the first instance we say that as if both the things are operating, the irreversibility comes only through this component efficiency of turbine and pump. So, in that case what may happen is that in a turbine process, if the process goes in isentropic manner, so it is 1 to 2s, which is isentropic, and if it is non-isentropic, the process goes as a dotted line, it is non-isentropic. Now, same effect comes, that means instead of in the saturated liquid regions, the discharge may happen in the again further drop in pressure. So, it is comes at 3. So, it is a subcooled region which is 3. Now, if from 3 to 4, if the process has to happen, so this process is called turbine. Now, for pump, if this process has to happen in an isentropic manner, so we say 3 to 4s is isentropic and 3 to 4 is non-isentropic. So, net effect what we will see here, that in a non-isentropic turbine process your work output will be less, but in a non-isentropic pump process your one input will be more. So, this we are going to introduce through these expressions which is called as isentropic efficiency per turbine, which is a net work output per unit mass in an actual process divided by net work in output for an isentropic process. And through by knowing the information at the state points, we can frame this as eta T turbine efficiency as H1 minus H2 divided by H1 minus H2s. Now, similar way we can write down the pump efficiency, because pump your net work input is will be higher. So, which means that your isentropic work has to be lower. So, in the numerator side it is eta P, which is the isentropic efficiency of the pump, is H4s minus H3 divided by H4 minus H3, and this isentropic enthalpy difference can be calculated as V3 into P4 minus P3. Okay. So, this is all about the thermodynamic cycles analysis for a Rankine cycle and how you are going to introduce the irreversibility and losses in the component wise. So, with this basic background, let us try to solve some numerical problem. So, the first problem is again an ideal Rankine cycle, which says that saturated vapor enters the turbine at 8 megapascal. So, 8 megapascal means state 1. So, at this stage we say it is 8 megapascal. So, if you recall this ideal Rankine cycle, the circuit diagrams, saturated steam enters at 8 megapascal and saturated liquid leaves the condenser at 0.008 megapascals. So, at this stage the state 3, that is categorized at 0.008 megapascal. Net power output for the cycles. So, net power from this entire cycle, which is nothing but turbine work minus pump work, that is 85 megawatt. So, we need to find out the thermal efficiency, work ratio, back work ratio, mass flow rate of the steams and all. So, I have already given the expressions for these parameters. To solve this kind of problems, we have to first rely on the steam table. So, you must understand how you are going to find out the state points by looking at the steam tables from the data given in this problem. So, to know the exact state, so the ideal choice that we should draw this TS diagram first. So, in this TS diagrams we are going to locate all these points. So, process 1, 2 is turbine, 2 to 3 is condenser, 3 to 4 is pump and 4 to 1 is the boiler, and this is at 8 megapascal and this condenser process is at 0.008 megapascal. We all know 1 to 2 is isentropic, 2 to 3 is constant pressure, 3 to 4 is again isentropic, 4 to 1 is again constant pressure. So, from this data given, so what we first need to know is that use steam table and try to find out the points in this TS diagrams or state points definition you have to find out. So, we say saturated steam which is at 8 megapascal. So, this you can refer as saturated steam table based on pressure. So, at this point we can calculate its H1 as 2758 kilojoule per kg, and also we need S1 information, because to arrive at point 2 this is S2 is equal to S1. So, since S2 is equal to S1, so we need to find out what is S1 at 8 megapascal. So, this number is 5.7432 kilojoule per kg Kelvin. So, you have H1 S1, then point 2. So, at state 2 we can find out S2, and that is nothing but your S1, and that S2 is equal to SF plus X2 into SFG. SFG is nothing but SG minus SF. So, at this point we need this data, and from this data at state 2 we can recalculate, since S2 is equal to S1. So, it is a 5.7432 minus SF. SF is 0.5926 and SG minus SF is 7.6361. So, these data are obtained at 0.008 megapascal. So, this will give you the information about X2, and that is S2 minus SF divided by SG minus SF. So, X2 we find it out as 0.6745. This is the dryness fraction at state 2. Then state 3. So, once we know this X2, so we can find out H2 is equal to HF plus X2 into HFG, and this data will give you, and here also we have HF at this pressure is 173.88 kilojoule per kg, HFG is equal to 2403.1 kilojoule per kg. So, we get the information about H2, and this H2 is 1794.8 kilojoule per kg. Now, having said this, we have state 1, state 2 information, state 3. State 3 information is already inbuilt in HF and SF. So, from this it is we can find out H3 as 173.88 kilojoule per kg, and H4 is nothing but H3 plus V3 into P4 minus P3. So, P1 or P4 minus P3. So, this is 8 megapascal and this is 0.008 megapascal. So, from this we get H4 as 181.94. So, we have all the information which is required to calculate these parameters. So, let us go one by one. Thermal efficiency W net by Q in, and this information we can write it as H1 minus H2 minus H4 minus H3 divided by H1 minus H4. By inserting this number, this value is 37%. Second part is work ratio W net by Q in. So, this is H1 minus H2 minus H4 minus H3, Q in is H1 minus W net by WT turbine work. So, this is H1 minus H2. So, this number is close to 99. So, correspondingly back work ratio, that is W dot P by WT. So, that is H4 minus H3 divided by H1 minus H2. So, this number would be approximately 0.83%. So, you can see this number is too less. That means, this is the essential necessity that back work ratio should be as low as possible. Then mass flow rate of steam. So, you can say W dot cycle is equal to m dot into W dot net. So, from this cycle work what is given 80 megawatt, we require mass of steam. So, we can find out this m dot as W dot cycle divided by W dot net. So, this is, we have all the information, cycle network we know, and we know the cycle work, which is 85 into 10 to the power 3 divided by network is 955. So, this is nothing but the term 1, denominator part of this. So, this number would be 89 kg per second, and rest of the things we can find out. Q in is equal to m dot H1 minus H4. M dot we know. So, this number is 229.3 megawatt. Q out is equal to m dot into H2 minus H3. So, this number is 144.3 megawatt. And last part is cooling water. So, here what happens, this Q out which goes out of the condenser, it is taken away by this cooling water. So, we can make some assumption that at some temperature the cooling water enters and some temperature it leaves. A tentative practical number could be, inlet temperature could be 20 degree centigrade, outlet temperature of this cooling water will be, let us say 38 degree centigrade. Now, with these things we require what is the cooling water requirement. So, m dot W we can write it as Q dot out divided by CPW, specific heat of water, into delta T, that is T out minus T in. So, Q dot out already we have found out, and CPW that number is 144,300 divided by CPW is 4.18, delta T would be 18. So, this answer would be 1918 kg per seconds. So, what it sees is that steam flow rate or working fluid flow rate should be 89 kg per second, whereas for this 89 kg we require the cooling water 1918 kg per seconds. So, of course, this is a huge power plant producing 85 megawatt. Now, next problem which imposes the component efficiency. So, the component efficiency when it is introduced, we say the turbine and pump operate as 88% efficiency. Now, for that process, how this cycle is going to modify? We can redraw this cycle in a manner that which we can introduce the component efficiency. So, instead of 1 2, we say it is 1 2s, we say it is 1 2. Now, instead of 3 4s, we say it is 3 4. So, rest of the things remains same. So, we can extract all the data as H1 as 2758 kilojoule per kg, H2S is equal to 1795 kilojoule per kg. So, these informations are already there in the previous example. So, H3 is 174 kilojoule per kg, H4S is 182 kilojoule per kg. In addition to that, and here cooling water enters at 20 degree centigrades, leaves at 38 degree centigrades. Net work output from the cycle is 85 megawatt. So, W dot cycle. Okay. And compressor, that is eta P is equal to, and eta C, pump efficiency and turbine efficiency is 0.88. Now, with this informations, if you try to solve, so first thing we have to use these expressions, turbine efficiency as H1 minus H2 divided by H1 minus H2S, and this number is 0.88. From this data given, we can get back what is H2, actual condition of the steam leaving the turbine, and this value will be 1910.6. Similarly, pump efficiency, we can say it is V3 into P4 minus P3 divided by W dot P by M dot, and this is 0.88. So, this number we know. So, this will give you W dot P by M dot as 9.1 kilojoule per kg. So, from this also we can find out what is H4, which is H3 plus this term. So, this is 183.1 kilojoule per kg. Now, in the same method we can find out one by one thermal efficiency as W dot T minus W dot P divided by Q in. So, that is 2758 minus 1910.1 minus 9.1 pump work, that is 2758 minus 183.1. So, this is 32.6%. Then work ratio is W dot net divided by M dot divided by W dot T by M dot. So, we can find it out as 8. This information already in that previous problems we have these numbers, that is H1 minus H2, and this number is 98%. So, if you recall our previous data, problem data and this data, work ratio drops by only 1%. So, from 99 to it becomes 98%, and pump ratio or back work ratio in same number would be 9.1 divided by 847.4, this is about 1%. So, basically work ratio is the, even if you introduce the component efficiency, the does not have a significant implications on work ratio or back work ratio. Then mass flow rate of steam, M dot is W dot cycle by H1 minus H2 into minus H4 minus H3. So, this number we can calculate as 85 into 10 to the power 3 divided by 8, 38.8. This number we got from the previous example. So, it is 101.4 kg per second. In earlier problem it was 89 kg per seconds. So, by introducing component efficiency your steam consumption gets higher. And similar way we can find out Q dot in as 261 megawatt, Q dot out as 176 megawatt, that is in the boiler and this is in condenser, and cooling water requirement MW water is 2339. So, this number is also higher. So, we have seen that although first of all the efficiency drops, work ratio is not much affected, steam consumption rate is higher and cooling water requirement is also higher. Why? Because we have introduced irreversibility into the systems through its component efficiency of turbine and pump. So, that is again the basic need or analysis or design of a steam power plant. What it says is that under no circumstances it is advisable to drop work ratio, because it will not justify the utility of power. So, with this I conclude. Thank you for your attention.